Hey guys, how's it going? Mr. Mitchell here. In this video we're going to go over section 1, i.e. the multiple choice questions from the 2014 SQA National 5 Physics exam paper. Now there are 20 questions in this section and I recommend that you try them yourself before looking at these solutions. So let's get started. Question 1 says that the voltage of an electrical supply is a measure of the, and this is just asking us for the definition of voltage or potential difference from the electricity topic. Now remember that voltage or potential difference was defined as the energy supplied to each coulomb of charge passing through the supply or battery. Now the closest we have to that here is got to be this one here, D. So the voltage is the energy given to the charges in the circuit. So that means our answer for question 1 is D. Question 2 says that 4 circuit symbols W, X, Y and Z are shown, so that's them shown here, and it says which row identifies the components represented by these symbols. Well, this just comes down to you knowing your circuit symbols for different components. So first of all, W is a bulb or a lamp, so remember we can call it either. So we're going to call it lamp here because that's the word that they're using in the table. Remember the capital V inside the circle, that is your voltmeter for X. This box shape has got to be your resistor, and the box shape with a line straight through it represents the fuse. And remember that line going through represents the thin wire inside the fuse. So for W, X, Y and Z we had lamp, voltmeter, resistor and fuse. So we need to look for that combination here. So we have lamp, voltmeter, resistor and fuse for D. Question 3 says that a student suspects that ammeter A1 may be inaccurate. Ammeter A2 is known to be accurate. Which of the following circuits should be used to compare the reading on A1 with A2? Well, if we know that A2 is getting an accurate reading of current, but A1 might be inaccurate and you want to check it and compare it with A2, then you need to make sure that ammeters A1 and A2 are going to be measuring the same current. So the only way to do that is to ensure that ammeters A1 and A2 are on the same path. So if we look at A first of all, we can see that A1 and A2 are actually on different branches of this parallel circuit. So they may not be measuring the same current depending on the values of these resistors, which we don't know. So we can eliminate A from our options. For B though, we can see that A1 and A2 are actually both on the same branch or same path because this is a series circuit. So that means that if ammeter A2 is measuring the current in this branch and I know that one's accurate, then I can just compare my value that I get from A1 with the value from A2 because they should be exactly the same since current in a series circuit is the same at all points. And I don't need to go through the rest because you can hopefully see that A1 and A2 for C, D and E are actually on different branches. So that means my answer has got to be B. Question 4 says a ball of mass 0.5 kilograms is released from a height of 1.00 meters and falls towards the floor. And you can see that in the picture here. It then says which row in the table shows the gravitational potential energy and the kinetic energy of the ball when it is at a height of 0.25 meters from the floor. Well, if we look back at the picture, in order to get the gravitational potential energy at a height above the floor, we simply need to use the equation for gravitational potential energy using this height of 0.25 meters. So we have EP equals mgh, substituting in the numbers gives us 0.5 times 9.8 times 0.25, where 0.5 kilograms was our mass of the ball and 9.8 is the gravitational field strength on Earth. And we then have our height of 0.25 meters above the floor. So putting that into your calculator should give you an answer of 1.2 joules. However, to find the kinetic energy, we need to use conservation of energy here, because if we look back at the picture, remember we're saying that the ball falls from a height of 1 meter and it's now at a height of 0.25 meters. So the ball itself has actually fallen through a distance of 1 minus 0.25 meters, or in other words, 0.75 meters. So we're going to assume that the gravitational potential energy at the start is converted into kinetic energy for the ball when it moves, and we're going to assume no energy losses due to friction or air resistance. So by conservation of energy, we can say the kinetic energy EK is equal to the change in gravitational potential energy, which is equal to the gravitational potential energy at the start minus the gravitational potential energy at the height of 0.25 meters. So I'm going to write this out as mgh twice, but with subscripts 2 and 1 to represent the two different heights. So we have mgh2 minus mgh1 because the mass of the ball stays the same, the gravitational field strength G on Earth stays the same, and it's just the heights that are different. And we could either then just sub in the numbers, or you could actually factorize this to make it look a bit simpler. So because we've got identical mg terms here, we could introduce brackets and take the mg outside the brackets, like this. So this would equal mg times h2 minus h1. In other words, we've got the change in height that the ball has fallen through here. So if we sub in the numbers, we get 0.5 times 9.8 times 1 minus 0.25. In other words, that's the 0.75 meters from earlier, and you can put that into your calculator to get an answer of 3.7 joules. So a gravitational potential energy of 1.2 joules would give us an answer of either B or C, but we can see the kinetic energy that we found through conservation of energy was 3.7 joules, so that gives us an answer of C. Question 5 says that the pressure of a fixed mass of gas is 6.0 times 10 to the 5 pascals. The temperature of the gas is 27 degrees Celsius and the volume of the gas is 2.5 meters cubed. The temperature of the gas increases to 54 degrees Celsius and the volume of the gas increases to 5.0 meters cubed. What is the new pressure of the gas? Well, notice first of all that we have pressure, temperature and volume all changing here, which means that none of these variables are being kept constant, which means that we need to use the general gas equation. So to find the new pressure, we're going to say that that is P2. So we have P1V1 over T1 equals P2V2 over T2, which is our general gas equation. And notice as well that we're given temperatures in degrees Celsius, but remember the general gas equation only works when the temperatures are measured in Kelvin, not degrees Celsius. So we need to change both of those temperatures into Kelvin by adding 273. So if we sub in the numbers into this equation, we get 6.0 times 10 to the 5 for the initial pressure P1 times 2.5 for the initial volume divided by T1, which was the 27 degrees Celsius plus the 273 to get it into Kelvin. And this is equal to P2 that we're trying to find times the 5.0 for volume V2 divided by the temperature T2, which was 54 degrees Celsius. But remember, we need to add 273 to get it into Kelvin. So if we simplify both sides, we could do the left-hand side in your calculator, so this numerator divided by the denominator to get 5,000. And then on this side, we have 5.0 times P2, which gives us the 5.0 P2 here, divided by 54 plus 273, so that is the same as 327. And now what we can do is we can multiply both sides by 327 to get rid of it from the bottom of this fraction here. So we get 5.0 P2 is equal to 1635000, and you'll find that just by doing 5,000 times 327. And then to get P2 on its own, we simply divide both sides by 5 to get P2 equals 3.3 times 10 to the 5 pascals. And you'll see that that is actually one of our options here, which is B. Question 6 says that a student is investigating the relationship between the volume and the Kelvin temperature of a fixed mass of gas at constant pressure. Which graph shows this relationship? Well, this question is referring to Charles's law, which is the relationship between the volume and the temperature of a fixed mass of gas. And you should remember that for Charles's law, it says that for a fixed mass of gas at constant pressure, volume is directly proportional to temperature when it's measured in Kelvin. So we just need to find the one that represents directly proportional relationship here, and that is going to be shown by graph A. And that's because, remember, a straight line through the origin means that as one variable increases, the other one increases at the same rate. So that is shown by this straight line, which means it must be A. For B, that is not a directly proportional relationship. For C, this shows that volume remains constant as temperature increases, which is not the case. And for D and E, we have these sort of non-linear scales where we've got curves, which just isn't the case. So graph A shows us that as temperature increases, volume increases, or as temperature decreases, volume decreases. Question 7 says a liquid is heated from 17 degrees Celsius to 50 degrees Celsius. The temperature rise in Kelvin is. Well, for this question, you need to remember that a temperature change in Kelvin is the same as a temperature change in degrees Celsius. So if we want to find a temperature rise in Kelvin, then it's going to be the same as the temperature rise in degrees Celsius. So all we need to do is find a change in temperature delta T by taking one temperature away from the other. So we could write that as T2 minus T1, which gives us 50 minus 17, which is 33 degrees Celsius. And this is going to be the same as the temperature rise in Kelvin. So it's going to be a change of 33 Kelvin, which is going to give us answer A. Question 8 says that the period of vibration of a guitar string is 8 milliseconds. The frequency of the sound produced by the guitar string is. Well, remember from the waves topic, we have an equation relating the frequency and the period of a wave, and this is given by the period t equals 1 over the frequency, t equals 1 over f. So we could simply rearrange this first of all, or sub in the numbers first, it's totally up to you. But if I rearrange this to get f on its own on the left hand side, I can simply cross multiply or swap the f and the t here. So I get f equals 1 over t. Or a longer way to do that would be to times both sides by f, but then you would have tf equals 1. and then you would divide both sides by t to get f on its own. So that gives you f equals 1 over t, and then we can sub in the numbers. But remember, this is 8 milliseconds, so we need to be aware of the prefix here. So we have this equals 1 divided by 8 times 10 to the minus 3, because milli, remember, is divided by 1000 or times 10 to the minus 3, and you can put that into your calculator to get a final answer of 125 Hz, which gives us an answer of C. Question 9 says that a student makes the following statements about microwaves and radio waves. Statement 1 says that in air, microwaves travel faster than radio waves. Statement 2, in air, microwaves have a longer wavelength than radio waves. And statement 3, microwaves and radio waves are both members of the electromagnetic spectrum. Which of these statements is or are correct? Well, let's go through each of these statements in turn and decide whether they are true or false. So for statement 1, in air, microwaves travel faster than radio waves. That is false, because remember, microwaves and radio waves are both members of the electromagnetic spectrum, which sort of answers statement 3 for us, but that means that both of them have to travel at the same speed, and that speed is the speed of light, 3 times 10 to the 8 meters per second, or 300 million meters per second. For statement 2, in air, microwaves have a longer wavelength than radio waves. This is false as well, because remember, radio waves have the longest wavelength on the electromagnetic spectrum, and the way I like to remember that is that one wavelength for a radio wave is roughly the size of a football pitch or a mountain range. For statement 3, microwaves and radio waves are both members of the electromagnetic spectrum, and we said that this was true earlier just from knowing your members of the electromagnetic spectrum, and this means that we have statement 3 only is correct, which means our answer is B. Moving on to question 10, which row describes alpha, beta and gamma radiations? Well, this just comes from knowing the definitions of your alpha particle, beta particle and your gamma ray. Well, first of all, for the alpha particle, remember this consists of 2 protons and 2 neutrons, which is also the same as a helium nucleus. So that means our answer is going to be either A or B. And for beta, remember a beta particle is a fast moving electron. So that means it's got to be either B or E here, but we said it was either going to be A or B initially, so it's looking likely that the answer is going to be B. But let's just check gamma. So remember, a gamma ray is a high frequency electromagnetic wave, which means it is electromagnetic radiation, which means it's got to be either B or C here. So it's looking like B is our answer here, because alpha is the helium nucleus, beta is the electron from the nucleus, and the gamma ray is the electromagnetic radiation. So our answer is B. Question 11 says a sample of tissue is irradiated using a radioactive source. A student makes the following statements about the sample. Statement 1 says the equivalent dose received by the sample is reduced by shielding the sample with a lead screen. Statement 2 says that the equivalent dose received by the sample is increased as the distance from the source to the sample is increased. And lastly, statement 3 says the equivalent dose received by the sample is increased by increasing the time of exposure of the sample to the radiation. Which of these statements is or are correct? Well, let's go through each statement again and decide which ones are true or false. For statement 1, the equivalent dose received by the sample is reduced by shielding the sample with a lead screen. That is going to be true because remember, lead is a good shielder or absorber of radiation. That's because it's going to absorb alpha, beta and most of gamma. But remember, some gamma rays will still get through lead because it's not a perfect absorber of gamma rays. But it's going to do a good job of reducing the equivalent dose or the exposure to the radiation. Statement 2, the equivalent dose received by the sample is increased as the distance from the source to the sample is increased. Well, this is suggesting that you're getting further away from the source and that the equivalent dose is going to increase. But that is the opposite to what would actually happen, because remember, the closer you get to a radioactive source, the more exposure you're going to get to that radiation. But a good way to protect yourself from radiation is to be further away from the source. So this is going to be false because it's actually the opposite is true. And lastly, statement 3, the equivalent dose received by the sample is increased by increasing the time of exposure of the sample to the radiation. Again, this is true because this is not going to protect you from radiation. If you're exposing yourself to the radiation for longer periods of time, then you're going to be exposed to a higher equivalent dose. So this means we have statements 1 and 3 that are correct, which gives us an answer of E. Question 12 says that the half-life of a radioactive source is 64 years. In 2 hours, 1.44 times 10 to the 8 radioactive nuclei in the source decay. What is the activity of the source in becquerels? Well, we've got a time here and we've got the number of nuclei, so we can use the equation for the activity of a radioactive source, which is A equals N over T, where A is the activity, N is the number of decays, and T is the time. But remember, time in this equation must be measured in seconds, not in hours, so we need to convert this 2 hours into seconds. So we can substitute in the numbers here with 1.44 times 10 to the 8 for the number of decays or number of nuclei that are decaying, divided by the number of hours in seconds. So we have 2 times 60 times 60 to get it into seconds. So 2 times 60 gets it from hours into minutes, and then times by 60 again gets the minutes into seconds. And putting that into your calculator should give a final answer of 2 times 10 to the 4 becquerels. And this means our answer is option A. Question 13 says that a student makes the following statements about the fission process in a nuclear power station. Statement 1 says electrons are used to bombard a uranium nucleus. Statement 2 says the heat is produced, and Statement 3, the neutrons released can cause other nuclei to undergo fission. Which of these statements is or are correct? Well, let's go through each statement in turn and decide whether they're true or false. So in a nuclear fission process, it says electrons are used to bombard a uranium nucleus. That is false because remember, it's not electrons, it's actually neutrons for induced fission. So neutrons are instant on a uranium nucleus, causing it to undergo fission and split apart. Heat is produced, that is true, because in both the nuclear fission and fusion processes, energy is released in the form of heat. So we can put a tick next to that one. And lastly, statement 3, the neutrons released can cause other nuclei to undergo fission. That is true because remember, that is what happens in a chain reaction. Neutrons that are released from one nuclear fission reaction can go on to hit other uranium nuclei, causing them to split apart and more neutrons to be released, and the process repeats. So this means we have statements 2 and 3 that are correct, which means our answer has got to be E. Question 14 says which of the following contains 2 vectors and 1 scalar quantity? Well, let's look through each of these and decide whether they're scalars or vectors. Well, firstly, remember a scalar quantity is one that has a magnitude only, and a vector quantity is one that has both a magnitude, i.e. a size, and a direction. So acceleration, that is a vector quantity, mass is a scalar quantity, and displacement is a vector quantity. So it's looking like A as our answer here, but let's just look at the rest. So displacement, that is a vector, force is also a vector, and velocity is a vector. So there's 3 vectors there, so that is not going to be the answer. For C, we've got time, that is a scalar, distance is also a scalar, and force is a vector. So we have 1 vector there and 2 scalars, so that's not the answer. For D, we have displacement, velocity, and acceleration, which again, they are all vectors. And for E, speed, velocity, and distance, well, speed and distance are scalars, and velocity is a vector. So this means our answer has got to be A. Question 15 says a vehicle follows a course from R to T as shown. So the vehicle starts off at R, travels 2.4 kilometers south to reach S, and then travels another 1.0 kilometers west to reach T. The total journey takes 1 hour. Which row in the table gives the average speed and the average velocity of the vehicle for the whole journey? Well, remember, speed is a scalar and velocity is a vector, so we're looking for a direction as well as a magnitude for the velocity column, but we're only looking for a magnitude, i.e. a size, for the speed column. So we can rule out answers A and C straight away because we don't need a direction for the average speed because it's a scalar. So to find average speed, remember we can use the equation D equals V bar T, where V bar is our average speed and D is the total distance travelled. And rearranging this for V bar, the average speed, we get V bar equals D over T. So we can see the total distance travelled by the vehicle is 2.4 kilometers plus 1.0, which gives us 3.4 kilometers. So substituting in the distance 3.4 kilometers and the time of 1 hour, we're going to get a speed in kilometers per hour, which is what we want here because that's what the units are in the column for average speed. So we get 3.4 kilometers per hour. Now remember, we ruled out A and C because those had directions, and we can also rule out B here because it's obviously not 3.4 kilometers per hour. So we've narrowed it down to D or E here, but we need to do some more work in order to find out what the average velocity is. So in order to find the average velocity, remember this uses displacement as well as time. So in order to get the displacement, we need to do resultant vectors, and you can either use the scale diagram method or the calculation method. I'm going to use the calculation method with Pythagoras, but let's draw a little sketch of our diagram. So from the initial picture, we already have the vectors joining nose to tail. So we had this vector, which we'll call A, which is 2.4 kilometers, and we had this other vector here joining on nose to tail with a length B of 1.0 kilometers. And what we're going to do is find the resultant vector, which looks like this, which we can add 2 arrows onto to show it's the resultant vector. And we're trying to find the unknown side C, which is the hypotenuse. Let's just label the right angle in there and also the angle that we want here for the direction. So angle theta will be in here, and the reason it's in there is because remember we always define the angle theta next to the starting point. So we start off here, so this has to be the angle in here. To find the magnitude of vector c, we can use Pythagoras. So we have c squared equals a squared plus b squared, which equals the 2.4 squared plus 1.0 squared, which equals 6.76. So c is equal to the square root of that, which equals 2.6 kilometers. And then for the direction, remember we need to use tan theta equals opposite over adjacent. So this gives us tan theta equals opposite is 1.0 divided by adjacent is 2.4, which equals 0.42. And now to find the angle theta, we do inverse tan or shift tan in your calculator of 0.42, which gives us roughly 23 degrees. But remember that is just telling us this little angle in here is 23 degrees. But the actual direction as a bearing, remember, is going to be defined from north, from 0, 0, 0 as a bearing. So drawing a vector round from here all the way round until we get to the resultant vector is going to give us 180 from this section plus the 23 degrees. So that means I can write my resultant displacement as 2.6 kilometers at 203. And remember, we don't need the degree symbol for a bearing. So now we've got the displacement and the direction. We can use our equation for average velocity, which is s equals v bar t. Rearranging for v bar, we get v bar equals s over t, which gives us 2.6 over 1, which is 2.6 kilometers per hour at the angle of 203, not forgetting to include the direction for average velocity that we just worked out. So this means we've got 3.4 kilometers per hour and 2.6 kilometers per hour at a bearing of 203, which means our answer is E. Moving on, question 16 says that a force of 10 newtons acts on an object for 2 seconds. During this time, the object moves a distance of 3 meters. The work done on the object is, well, remember our equation for work done, EW equals F times D, so we can substitute in the numbers for the force of 10 times the distance of 3 meters, and that's simply going to give us 30 joules. So our answer is D. And notice that the 2 seconds there, the time, is a distractor. You didn't need to use it to find the final answer, it's just there to put you off. Question 17 says catapults are used by anglers to project fish bait into water. A technician designs a catapult for this use. Pieces of elastic of different thickness are used to provide a force on the ball. Each piece of elastic is the same length. The amount of stretch given to each elastic is the same each time. The force exerted on the ball increases as the thickness of the elastic increases. And that last statement there is going to be really important for this question. It then says which row in the table shows the combination of the thickness of elastic and mass of ball that produces the greatest acceleration. Well, remember we just said that the force exerted on the ball increases as the thickness of the elastic increases. So the bigger the thickness of the elastic, the bigger the force. So we can sort of think about this column here for thickness of elastic as actually telling us about the force. So the bigger the thickness, the bigger the force. So that means the force gets bigger as we go down here. Now we've also got the mass of the ball, and you should be thinking that if we've got something to do with force, mass and acceleration, it's dealing with Newton's second law, F equals ma. But let's just rearrange this to get the effect on the acceleration, so let's rearrange for A. So we get A equals F over m, which is the force divided by the mass. So which row in the table will show the biggest acceleration? Well, the biggest acceleration is going to be found from the biggest force, because this is on the numerator of the fraction, and from the smallest mass. So which combination has the biggest force and the smallest mass? Well, first of all, the biggest force is going to be from the biggest thickness of elastic, because remember we were told that in the question. So it's going to be D or E here, the biggest force or the biggest thickness. And we want the smallest mass to give us a bigger value on this side. So the smallest mass is going to be the 0.01 kilogram mass of ball. So this means our answer is D. Question 18 says that a spacecraft completes the last stage of its journey back to Earth by parachute, falling with constant speed into the sea. The spacecraft falls with constant speed because the gravitational field strength of the Earth is constant near the Earth's surface, it has come from space where the gravitational field strength is almost zero, the air resistance is greater than the weight of the spacecraft, the weight of the spacecraft is greater than the air resistance, or the air resistance is equal to the weight of the spacecraft. Well, this idea is getting at Newton's first law of constant speed or balanced forces. So remember, an object will travel at a constant speed when there's balanced forces acting on it, and the only one that is referring to balanced forces here is E. The air resistance is equal to the weight of the spacecraft. So remember, the weight of the spacecraft will act downwards, and the air resistance will act back up the way. So both of these forces will be balanced to cause the spacecraft to fall with a constant speed. Question 19 says that a ball is released from point Q on a curved rail, leaves the rail horizontally R and lands 1 second later. The ball is now released from point P. So initially the ball is released from point Q here and will land at this point here with a horizontal range of 2 meters, i.e. a horizontal distance travelled of 2 meters. But when the ball is released at P, we need to work out what's going to happen. So it says which row describes the motion of the ball after leaving the rail. So we've got time to land after leaving the rail and distance from S to landing point. So remember S is over here to the landing point, so we need to work out whether the horizontal range or horizontal distance of the ball is going to change if it's released at a higher point on the curved rail, and we also need to work out if the time of flight of the projectile is going to change. Well, first of all, the time to land after leaving the rail has got to be the exact same as the time for the ball released from point Q, and that's because remember the time of flight for the horizontal motion and vertical motion of a projectile are the same. In other words, a projectile will take the same time to travel horizontally as it does vertically, so it doesn't matter if the ball is released from a higher point, it's going to take the same time to travel horizontally that it does vertically, which will be 1 second. So this means our answer is either going to be A or C. And we now just need to work out whether the ball is going to land less than 2 meters or more than 2 meters from point S. If we move the ball up from Q to point P, it's going to have more gravitational potential energy. So when we let it go, that gravitational potential energy is going to change into kinetic energy, and therefore when the ball reaches point R, it's going to have a greater speed than the ball when it was released at point Q. So when the ball passes point R, it's going to have a greater horizontal velocity at this point, and therefore it's going to travel further than the 2 meters and land down here somewhere. And you can think about that from the equation for horizontal motion of a projectile, speed, distance, time, d equals vt. So if the time's the same at 1 second and the horizontal velocity v is bigger, then the horizontal distance or range has to be bigger as well. So we have 1 second and more than 2 meters, which gives us an answer of C. Lastly, question 20 says that a solid substance is placed in an insulated flask and heated continuously with an immersion heater. The graph shows how the temperature of the substance in the flask changes in time. So we have temperature in degrees Celsius on the y-axis and time in minutes on the x-axis. It then says after 5 minutes the substance is a solid, liquid, gas, mixture of solid and liquid, or mixture of liquid and gas. Well, let's look at the graph for after 5 minutes. So when we've got the zigzagging up the way, this is a heating curve. So we start off with our solid substance here, we heat it up until it reaches its melting point, at which point it's going to start melting and turn from a solid into a liquid. So we have solid going into a liquid here along this constant temperature, and then we reach 6 minutes, at which point all of the solid has melted into a liquid, and then we start increasing its heat again for the liquid up until 10 minutes, at which point the liquid will reach its boiling point, and then it will start changing into a gas at a constant temperature until 30 minutes. And the bit we were interested in was the 5 minutes, which is between the 2 and the 6 minutes, around here somewhere. And we said that at this point we're going to have a solid changing into a liquid, but it's not completely changed into a liquid at the 5 minutes. So we could say that at that point we've got a mixture of solid and liquid. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video one of these, subscribe to the channel, and I'll see you in the next one. Take care.